So we stopped last lecture at discussing the dictionary abstract data type, and we said a dictionary is a collection of elements, and we want three operations in the dictionary: lookup, insert, and delete to be efficient. We have we have explored the use of the concrete data structures that we know of: sorted arrays, unsorted arrays, sorted lists, and unsorted linked lists, and we have found that the efficiency of the three dictionary operations is not quite what we want using these three data structures. And that's because a dictionary is a data structure where we perform a lot of lookups, a lot of inserts, and a lot of deletions. Just imagine a dictionary which is used to implement some sort of a huge database, like a big online shop, for example, like Amazon, where customers all the time they're looking up for items. They are or the Amazon themselves, they are inserting in new items, deleting old items, updating stocks, etc. So these things they happen all the time and in large amounts. So we need these operations to be efficient. Doing something linear once in a while, it's okay. However, you cannot do it all the time. So if lookup is happening a lot of times, insert happening a lot of times, then linear is not good. So this is why we needed the new data structure in order to implement the dictionary. And this is what we will see in today's lecture. Today's lecture we will see a new data structure that we call tree. Okay, so a tree is something like that. It grows backwards. So a tree has one distinctive node, which is the root. This is called the root of the tree, and a root has got child nodes. So this is the root. This is a child of the root, and these are children of this node. Okay, and these are siblings of this node. Okay, so we have a node, as you can see. So this is a node. This is the parent of X. These are the children of X. These are the siblings of X. So a tree starts with the root and then has children, and each child has other children, and so on. Each node has got what we call a depth. So root is at depth 0. Okay, the depth of the root is 0. So this is depth 0. This is depth 1. This is depth 1. This is depth 1. This is depth 2. This is 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 depth 3. Each node has got only one parent. It's a tree. If it doesn't have only one parent, if it has two parents, that would be a graph. So in a tree, each node has got one parent only. A node can have any number of children from 0 to anything. Okay. So if a node has 0 children, we call it a leaf. Basically, just like a tree, you have the trunk and you have branches, and at the end of the branches you have leaves. So this is a leaf, this is a leaf, this is a leaf, this is a trunk, and you have branches, and at the end of the branches you have leaves. So this is a leaf, 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 and this is a leaf. These are all leaves of the tree. The nodes that are not leaves, they are called internal nodes or interior nodes. Okay, so that's the tree. So again, a tree has got a root, which is the starting node. Obviously, a tree can be empty, so a tree can be just null. Okay, this is also a tree. Okay, a tree has only one node. This is a tree. That's a tree. Okay, that's a tree. That's not a tree, because a node has got more than one parent. That's a graph, actually. It's not a tree. So trees, they have nodes which are connected to each other, such that a node has only got one single parent only, and they grow from top to bottom. The first node where the tree starts growing is called the root, and it is at depth 0. The other nodes are at superior depths. So depth 1 and depth 2. We call this level 1. So it's depth 1. This is the level 2 of nodes, and so on. Okay, and these are leaves, and these are interior nodes. The number of edges, this is called a node, this is called an edge. Okay, the line that connects two nodes is called an edge. The number of edges that come out of a node is called the out degree of a node. Okay, so a node has got an in degree and has got an out degree. The in degree is the number of edges that come to the node. So in a tree, the in degree is always 1. Okay, there's always one edge coming to the node. The out degree is gonna depend. So this node has got an out degree 0. This node has got an out degree 0. This node has got an out degree 3. This node has got an out degree 2, and so on. I call it in the shape just degree because in degree is always 1. So we just say degree, and when we say degree we mean out degree because it's a tree. So this is all we need to know about the tree as a shape, and the properties that exist in the tree. Now, a special case of a tree is a binary tree. So we said a tree can have, each node can have any number of children. So that's a tree. The root has 3 children. This child has 0. This child has 1. This child has 0. But this is not a binary tree. A binary tree is a tree where each node has 2 children at most. Okay, so each node has only got 0 or 1 or 2 children. So that's a binary tree. So this is a binary tree, or 2 children. So that's a binary tree. So this is a binary tree because each node has got only 0 or 1 or 2 children. So this one has got 0 children. This one has got 0 children. This one has got 2 children. This is a binary tree because we said this one is a binary tree, and this one has got 1 child, so it's okay. This one is a binary tree, right? This one isn't a binary tree because this node here has got 3 children. So this is a binary tree. So a binary tree is a tree where each node has got at most 2 children, i.e. has got 0 children, 1 child, or 2 children. Now, a binary search tree is a binary tree, okay? However, it has got keys, it has got elements of the dictionary inside it, organized in a special way. Okay, so let's not get lost. We have seen a tree, and then a special case of a tree is a binary tree, and then a special case of the binary tree actually is a binary search tree, which is the most important tree for us in order to implement the dictionary abstract data type. So a binary tree is a tree with the condition that each child has got at most 2 children. A binary search tree is a binary tree such that but the elements inside the tree are organized in a specific way that we will see. These nodes here, they hold records. Okay, so this is like when we saw a linked list. We represented the linked list like that. This is the head of the list, and these are the elements. Each element is a record. So the same applies here. This is the head of this is the root. This is the head of the tree. These here, they have empty pointers. They don't point to anything. So it's similar to the linked list, but it has a tree structure, right? So we have records pointing to other records. We can implement it as an array, as we will see, but just to explain to you what are these circles. So these circles, which we call nodes, we are going to put data inside them. So they are going to be the elements of the dictionary. So we said we have a dictionary, a collection of elements, and the elements are actually these nodes. So back, we've seen a tree, we've seen a binary tree, and now we're going to see a binary search tree. So what's a binary search tree? It's just a binary tree where we are going to put elements. We said an element has got a key and a value. Okay, an element of a dictionary is a key plus value. And like we did before, we are going to use the keys to represent. We are only going to use the keys to represent the elements. So the element is something like key is 7, and there is some data as well here. But we are not going to represent the data in the tree. So when you see this node having 7 in it, it's actually the key 7 plus some data. So to avoid clutter, we are going to use the keys only. So a binary search tree, this is a binary search tree. So a binary search tree is a binary tree. I mean, as you can see, you can check it's a binary tree. Every node has got at most 2 children. So a binary search tree is a binary tree with the following property. In every node, the keys which are to the left are smaller than the node, and the keys which are to the right are larger than the node. Okay, not just the root, everywhere. Okay, so as we can see here, so this is 7, and everything to the left of 7, when we say to the left, we mean the left subtree. We call this a subtree. Okay, so this is a tree, and this is a subtree, and this is a subtree. This is the left subtree, and this is the right subtree. Okay, so all the keys in the left subtree are smaller than 7, and all the keys in the right subtree are larger than 7. And then we look at this node here. And what is the subtree of this node? The node 4, what is the left subtree of node 4? Well, this is all the left subtree. Okay, the tree that grows from the left of the number 4 is the left subtree. So the whole thing is the left subtree, and the right subtree is 5. Okay, so all the nodes which are in the left subtree of 4 are smaller than 4, and the elements which are in the right subtree of 4 are larger than 4. And again, for 15, the left subtree of 15 contains that element, and the right subtree contains that element, and we can check that the property of the binary search tree holds here, which means that the elements in the right subtree are larger than this, and the elements in the left subtree are smaller than the root. Smaller than the node itself. So this is the binary search tree. Okay, just to check our understanding quickly. Is this a binary tree? Now, let's say that our dictionary has got the elements from 1 to 9. Okay, so, or from 1 to 10. So our dictionary contains the elements with keys 1 to 10. And I want to put these elements inside this with keys 1 to 10. And I want to put these elements inside this binary tree such that it becomes a binary search tree. So how do I put the elements from 1 to 10 inside this tree? What do I put here? 5. Why 5? It's because we have 10 elements and we need 4 elements smaller than 5, and we need 5 elements, we have to put an element here, x. We need 4 elements smaller than x and 5 elements larger than x. So what is x which is going to satisfy this constraint? It's the element 5. Now what do I put here? 2. If you put 4, you have run out of elements, because if you put 4 here, then what are you going to put here? The number you're going to put here must be larger than 4 and must be smaller than 5. But you don't have enough now. So if you put 2 here, it's fine. So naturally, the only one left here is 1. So what do I put here now? 4. And here? 3. And what do I put here? 9. Okay, I would say this element is to the right. This is the rightmost, so it's the largest. So it's easy for me to put, if I put 10 here, then it's safe to put 9 right here. And the next smaller than 9 is 8. And then if we put 6 here and 7 here, because 6 and 7 are to the left of 8, so they are smaller than it. So this is what is the binary search. This is a binary search tree that represents the dictionary here. Right. So that's a binary search tree, and we know how to put elements inside a binary tree in order to make it a binary search tree. It's quite easy, an easy activity. Now, the binary search tree is an abstract data type, and we need to implement it using pointers or an array. Basically, we can program it. We can program it in our computer using a contiguous data structure or a linked data structure. This is what we saw last time. Anything that we have, we can either put it as one big chunk in main memory next to each other, and hence it's a contiguous data structure. We can do it by an array, or we can use pointers. And it occurs, or it happens, that we can use both arrays and pointers in order to implement a binary search tree. So how do we do that using an array? So let's assume this is our binary search tree. We can check that it is a binary search tree because it's a binary tree first, and then in every node, the element to the right of the node, in the subtree to the right of the node, are larger, and the elements in the left subtree are smaller. So it's fine. It's a binary search tree. Now, how do we? In the left subtree are smaller, so it's fine. It's a binary search tree. Now, how do we put it inside an array? Let's say we have the following array. So this is an array of 15 elements. So these are the indices of the array from 0 to 14. It's an array of 15 elements. And here is where we are going to put the content of the tree. Right? So what do we do first is that the first element of the tree, the root element of the tree, is going to go into the first slot of the array. So 7 goes to index 0. So we copy it over here. Simple as that. And then we look at the next level. Basically, we look at the children of the root. So the children of the root are 4 and 15. So we are going to put them in the next two slots. 4, we start with the left child, and then we put the right child. And then we look at the next level, and we put the elements 1, 5, 8, 19. Okay, and then we look at the next level, which I don't show here. So the next level is that. The next level is not as intuitive as the previous levels. Here, 1 should have a child, but it is empty. 5 also should have a child, but it's empty. Here should have a child, but it's empty. This one should have a child, it's empty. And this one is empty, and this one is empty, and this one is empty. And this is why, whenever there is an empty child, we are using a space filler -1. So again, if you remember, we look at the level and we copy it. And now we look at this level and we copy it. So the empty child becomes -1, 3 is 3, and everything else is empty. Now, why do we need to record the empty files, the empty nodes? It's because we want a contiguous data structure, and it's because we need to perform the operations in order to find what is the parent. Because in a tree, we always want, if we know the current node, we want to know the children of the current node, and we want to know the parent of the current node. Okay, this is important in the tree. So in the tree, it's always important, if we are at some node, I want to know what is the children, or what are the children of the node, and what is the parent of the node. This is like in a linked list, I need to know the next pointer. Okay, I need to know what is the node after me. And in a doubly linked list, I need to know what is the node before me. So tree, in order to traverse a tree, sometimes we are at some node, we need to go down, so we need to know the children, and we need to go up, so we need to know the parents. So here we use simple equations in order to find that. If we use an array in order to implement the tree, we can use simple equations. So if the node is I, if the node is at index I in the array, for example, if the node is at, let's talk about 4. So the node 4 is at index 1. So the node 4 is at index 1. Okay, so I equals 1 in this case. So the parent is at 1 minus 1 over 2, and we take the bottom of that, floor of that, and that will be 0. The left child is at 2 times 1 plus 1 equals 3. The right child is at 2 times 1 plus 2 equals 4. So these equations are telling me that the parent of the node which is at index 1, so the parent of the node at index 1, which is 4, is situated at index 0. So this is parent. And the left child is situated at index 3, and the right child is situated at right child is situated at index 4. Now, is that true? So this is 4, and the parent of it situated at index 0, i.e. 7. 7 is indeed the parent of 4, and left child situated at index 3, and the node recorded here is 1, and indeed it's the left child of 4, and then 4, or the node stored at index 4, which is 5 in this case, is the right child, and yes, 5 is the right child of the node 4. So, as you can see, if we put the tree inside the array, level after level after level, then we can index the parent and the children of every node in the tree. Yes. Say it again. Your question is about the number -1. This equation. There is so much background noise, I hardly hear anything. I think some students are talking or something, but I don't hear you well. Can you repeat the question? You mean the keys of the dictionary? Oh my God, this is so much noise. You mean can the keys of the dictionary be negative numbers? That's the question. Okay. So can the keys of the dictionary be negative numbers? Yes. In this case, we have to choose another. We have to use another space filler here. Okay. Okay. If your question, if the keys are negative, what number do we choose instead of -1? Well, you can have a null pointer here. You can choose to have a null pointer if you want, or you can agree on some number which does not occur in the dictionary. So you have a dictionary, it has lots of keys. You are going to make one specific number that you are going to use in order to denote the empty cells. Okay, so you can use integers and have one specific number, or you can use instead of integers here you can use pointers to records, and each record holds the key, and for empty records you just have a null pointer. So these are all little implementation issues that you can decide by yourself. Okay, so if we go back to what I was saying, we fill in the tree level by level inside our array, and this filling level by level allow us to use these equations in order to navigate through the tree from top to bottom, or bottom to the top. The problem with this representation, with this array representation of the tree, is that we waste a lot of space. Okay. So the problem with this array representation is that we are wasting a lot of space on the empty records here, but we need to put them in, otherwise these equations are not going to work. Okay, so that's the problem with the array representation. However, if the tree was something like that, then we do not waste space at all, because everything, there will be no -1 at all, basically. Okay, because the tree is full. However, if the worst case is if the tree is something like that, this is a binary tree, by the way, then a -1 is here. We have to fix that, a -1, and -1 here, and 2 -1s here, or whatever you use, and 2 -1s. So you keep filling the array with -1s, and this is not efficient because you only have 5 nodes, right? And the amount of space that you're gonna need with -1 is exponential. So representing a tree as an array is sometimes useful. We're gonna see that in heaps if we manage to do them. So representing a tree or a binary tree, in this case a binary search tree, as an array is fine